up to our second speaker, Steve Rittle.
Thank you. It's great to be here at the second SCAR Horizon Scan in 2065. To look back at 50 years of Southern Ocean science, I gather the participants were so exhausted after the first one, it took 50 years. In the 50 years leading up to the first scan, the biggest developments in Southern Ocean science were technology driven. We had satellites that could provide global measurements for the first time, autonomous instruments that measured the ocean in a way that was not possible before, and new sensors. And in the last 50 years, from 2014 to 2065, the same is true. We're now measuring the ocean with fleets of tens of thousands of autonomous vehicles that are fueled by nuclear batteries that have decade-long missions and measure everything, the entire ocean from surface to the deep ocean, including beneath the sea ice and in the ice shelf cavities. They measure a range of physical, biological, and chemical properties that were inconceivable in 2014. For example, environmental DNA and proteomics tell us not only what's there, but what it's doing, measured by these vehicles in real time. The ships are still needed. Most of them are sail-powered now. But they lower instruments that in 2014 were at the size of several buildings, and they measure the things that the submarines can't measure. The science has changed because we're actually measuring the phenomena that we're trying to understand, which in 2014 was still a bizarre idea. So what have those measurements told us? Well, they've confirmed the role of the Southern Ocean in a global system, climate and otherwise. But what have they said? What's happened to the Southern Ocean environment over the last 50 years? Well, it's warmed, unsurprisingly. The surface is 2 degrees C warmer than it was. The deep Southern Ocean is warming more rapidly than any other deep part of the ocean. It's now about 0.6 of a degree warmer at 1,000 meters than it was in 2014. Salinity has changed. It's fresher both near the surface and down deep, and that's because there's more precipitation as the global hydrological cycle has spun up in a warmer world. And the increased ice melt is also freshening ocean waters. Stratification has reduced. The change has been on the order of 10 or 20%. It's not huge. It's restricted a bit of nutrient input, and it's also restricted the amount of oxygen getting into the ocean. So oxygen levels have declined by about 15%. Sea level globally has risen by 30 centimeters relative to 2014. But the rate of rise is now double what it was then, and it's continuing to go up. Antarctic bottom water, which had already decreased in volume by 50% by 2014, is now extinct. There's essentially no water in the ocean that qualifies under the traditional definition of Antarctic bottom water. There's still some water sinking around Antarctica, but it's less dense than it used to be, and so that's maintaining the deep ocean oxygen concentrations. It's not going anoxic because there's no new water reaching the deep ocean. The major ocean currents have changed 10% or so, not huge changes. The subtropical gyres have shifted south, so in effect the size of the Southern Ocean has decreased over those 50 years. In terms of changes in the ocean circulation, what's probably of more importance is that ocean currents are now bringing warm water into the ice shelf cavities more effectively than they did before. And that's increased basal melt of ice shelves by a factor of 10. The thinning of the ice shelves has also allowed the ice shelves to float free of some of the seafloor topography. That's also led to easier ingress of warm water and further melting. So the ice shelves are melting more rapidly. Most of the changes I've talked about are not so dramatic, maybe 10 or 20% over 50 years. Part of the reason is that the Southern Ocean, its current systems and the fact that it can store a huge amount of heat continues to buffer high southern latitudes against against climate change. And so the rates of change are slower than in many other parts of the planet. The first 30 years between 2014 and 2045, there was a tug of war going on between the recovery of the ozone hole and greenhouse gases in terms of their effect on the atmospheric circulation. And so greenhouse gases were pushing the winds south and making them stronger. Ozone hole recovery was pushing the other way, and there was kind of a tug of war for 30 years. Greenhouse gases won, started shifting the wind south again, as well as the ocean currents. Unfortunately, in about 2040 or 2050, we, having not made any substantial action to mitigate greenhouse gas emissions, we began to inject sulfate aerosol into the stratosphere, which had the unintended side effect of forming a new ozone hole. So now ozone and greenhouse gases are working together to accelerate the rate of change. Many of the changes are modest, but not all. There are some big, profound, and rapid changes that have occurred in the Southern Ocean. As Helen will talk about, the marine ice shelf instability is no longer a theory, it's underway in glaciers in both West and East Antarctica. As a result, the IPCC 12th assessment report has increased the sea level rise estimates by a substantial factor. Perhaps of even more importance is that the absorption of carbon dioxide by the ocean has done us the service of slowing the rate of climate change, but at the cost of ocean acidification. By 2035, surface waters were undersaturated or corrosive to aragonite in winter. And by 2065, by today, the entire Southern Ocean from the surface to the seafloor year-round is corrosive to aragonite. Biological responses to this, Jose will talk a bit about, but they were a surprise in the sense that for some species, plasticity and rapid adaptation allowed organisms and communities to respond. In others, the combined effects of acidification, warming, lack of nutrient supply, and changes in ocean currents led to systems to cross thresholds and cause ecological regime shifts that were completely unanticipated. The rates, while the amount of change by now is perhaps not so worrying for some properties, the rates of change are rapid. And many of the changes are now irreversible, and we're committed to further change, which is now too late to reverse. Climate feedbacks that were speculated about and discussed at the first horizon scan have now kicked in. The Southern Ocean is absorbing less carbon dioxide than it used to, and that's tending to accelerate the rate of climate change. The ocean ice shelf feedback, sorry, I forgot to mention the changes in sea ice. How could I forget that? The sea ice, after decades of resistance, has finally begun to retreat. In February, by 2065, there's very little of the Antarctic margin which still has sea ice in summer. The winter changes are about 15 to 20%. A surprise in 2035 was the result from satellite measurements, the first satellite measurements to actually really measure sea ice thickness correctly, was that sea ice volume and sea ice thickness actually scale very well together, so the 50-year effort to try to measure sea ice thickness was largely a waste of time.
Just one question.
When we, at this second scan though, it's a sobering time to think about the decline in support for Antarctic science. Conserving the Antarctic environment is of as great importance as it ever was, if not more so, because it's now the last great wilderness theme park that's left on the Earth. And there are direct flights from many wealthy cities to Antarctica for holidays. But the pace of change and the consequences of those climate changes for the rest of the world, the non-buffered part of the world, are now so serious that Antarctic research is seen really as a sort of luxury that we could afford in the simpler times of 2014.